discussed how the charges divide and how the potentials divide. So charges divide on branching, potentials, the value of the potential divides on the capacitors or resistors or any devices interaction. See, now when I have individual capacitances, C1, C2, C3, C4, Cnth are connected in series. And V1, V2, V3, Vnth are connected. So I can calculate the net potential. The V equivalent will be V1 plus V2 plus V3 up till Vnth. So V equivalent will be C from here we can see this will be charge divided by C equivalent. The formula of potential is charge by capacitance. So V equivalent will be total charge is the same whether I write it for the equivalent part or the individual part. And this is C equivalent. For V1 I can say Q by C1. For V2 I can say Q by C2. For V3 I can say Q by C3. So up till Q for nth, it will be Cnth. So all the charges will get cancelled. Finally, 1 by C equivalent will be 1 by C1 plus 1 by C2 plus 1 by C3 up till 1 by C nth. This is the formula of the capacitance in series connection. Okay, so if you want to calculate the individual charge, total charge will be C equivalent into V. C equivalent means the net capacitance. V is the total potential. So C equivalent into V becomes the total charge. If you want to calculate the individual capacitances, you can use the charge. Charge will be the same. So you can use charge in any manner. C1, C2 for the different capacitors. If you put C1, you get the potential V1. If you put C2, you get the potential V2. So Q by C1, Q by C2, Q by C3 till Q by Cn. This is how you can calculate the potential for any cell. For any capacitor. Then energy, energy is half CV square. If you use C equivalent and the total potential, it will be half C equivalent V square. That means this will give you the total energy. For individual ones, you can use half C1 V1 square, right? Or you can use the formula half Q square by 2C. This is also valid. Let's practice a circuit based on this. Do one thing, write it till here, then we'll practice a circuit based on this. Please write it first. Done? All right, class. Let's continue with the numerical. See, here there is a circuit which is given. It has 5 farad, 10 farad. They both are connected in series, and various parts are given. So let us just solve part by part. See, the first one says that you have to calculate the C equivalent. So we can see here both of them are just connected directly. There is no branching. So we can conclude that they are connected in series. If they are connected in series, 1 by C equivalent will give us 1 by C1 plus 1 by C2. So 1 by C equivalent will be 1 by 5 plus 1 by 10. So this 1 by C equivalent will be, see this becomes 10, or directly we can even solve it. Yes, you can directly even write it. When you take the LCM, you have to take the reciprocal after it. So directly also you can write, or you can go step by step also. So I'll go step by step only. So this is 2 plus 1 divided by 10, that is 3 by 10. So this is not the answer because this is the reciprocal. You'll always need to convert it. This will become 10 by 3 farad. This will be the C equivalent value. All right. Second one says total voltage across the circuit. Since total voltage is already present here, you can see total voltage is given as 10 volt. So this is the total voltage. Then it says, third part says total charge stored. Now, total charge, you know the total voltage, you know the total capacitance. So if you multiply both of them, you will get the total charge. So total charge will be capacitance equivalent because we want the total charge. So it will be C equivalent into V. See, this is 10 by 3 into potential is 10. So this becomes 100 by 3 coulomb. This is the total charge. Now, the fourth part says charge stored in each. Plus charge in series remains the same. So even if you have 5 farad of capacitor, 10 farad of capacitor, if the total charge that has flown through it is 10 by 3, 100 by 3. So due to into the individual ones also, it will remain as 100 by 3 coulomb only. So this fourth one here, your Q1 will be equal to Q2, which will be equal to the main charge, that is 100 by 3 coulomb. All the charges will be the same. Why? Why is it same? Because this is a series connection. In series, all the charges, they remain the same. Okay. So this is the fourth one. Then it says voltage across each. Now, class, voltage will be different, right? When we were discussing the formula, that time also we saw the voltages will be different. How will we calculate V1? Charge is the same, but capacitors are different. This will be C1. Charge is 100 by 3. First capacitance is, let's say, 5. This becomes 20 by 3 volt. Similarly, when I'm calculating V2, V2 will be Q divided by C2. So Q is 100 by 3, C2 is 10. So this becomes 10 by 3 volt. Now, class, look at one thing. If I combine these both potentials are different. Total potentials are different. Okay, charges through each of them is the same, but voltages value are different. So if I add both of these, 20 by 3 plus 10 by 3, it will give me 30 by 3, which is equal to 10 volt. You are getting the 10 volt back, means your initially 10 volt came, which was the total voltage through the circuit, and it got distributed among 5 volt as 20 by 3 and as 10 by 3 in your 20 by 3 here and 10 by 3 in the 10 farad. This is how the voltage divided. Capacitances were different, but charge in each of them were the same. So this is how you have to calculate all of these questions in series or parallel. Write it down, then we'll see the series one. And all of you, please open the camera in the class. Okay, write it from here.
Ma'am, last one I'm not able to understand.
Voltage.
Yes.
See, capacitance is given as C1. Charge we have calculated across this, that is 100 by 3, right? So what is the formula of voltage? Charge
Q by
divided by capacitance, right? So see, charge is the same in all of these. Charge is at least the same, we know. So if charge is the same, so we'll put this as 100 by 3. But what about the capacitance? Capacitance is given C1. So if I put 100 by 3 by 5, I'll get the voltage across this one. Okay. Similarly, if I put C2, I'll get V2. Got it?
So we do summation of both.
No, we'll not do summation of both. That I was just telling you. See, I was just telling you, see, this is how the voltages are distributed. If you add both of these, you will get your 10 volt back. Means 10 volt was divided among two in this manner. One was 20 by 3, other one was 10 by 3. You don't need to add it. Okay?
Okay.
Please write it all of you. Then we'll do the parallel one.
Ma'am, second one is already given, right?
Yes, the total voltage is already present in the question. Done?
Ma'am,
Yes, Ubaidullah. Say,
here each means capacitor.
E, where?
Charge stored in each.
Yes,
So
yes.
this
Charge stored in each means in one capacitor each. Right. Means Q1 is for the first capacitor, Q2 is for the second capacitor. So for all the capacitors, the charges will remain the same here. Okay.
okay, ma'am.
Written.
Yes, ma'am.
Okay, let's continue with the parallel combination. See, in the parallel combination, the branching will be done. A single wire gets divided into various branches. So here, the charges will be split up because in the last class, when we were ending the class, we discussed this only, that charges divide on branching and potential isn't affected with that. So in this case, the potential doesn't get affected. So when I calculate the net charge this time, equivalent charge means total net charge. This will be Q1 plus Q2 plus Q3 plus Q4, Q5 till Qnth it will be added, right? N number of capacitors are there, so Qnth it will be added. Now we know the formula, its charge is equal to CV. So C is C equivalent, potential is there. Now potential will remain the same for Q1, means for the first capacitor, when I want to write the value of capacitance and potential, it will be C1 into V. Then for the second charge, I'll write C2 into V. For the third one, C3 into V. Like this for so on, C4, C5, C6 and all, they will be put till C for V. All the potentials will be cancelled, right? V from here it will be cancelled. So in parallel connection, you can just directly add all of it. No need to make it in the reciprocal. Okay, no need to put it reciprocally and add it. One by you don't have to do. Just add it C1 plus C2 plus C3 plus C4 up till Cnth. This is the whole formula. So that's why in the last class before I thought we didn't discuss this part. So for the series, I was just taking reciprocal addition, and for the parallel ones, we were just adding them. Now, individually also you can calculate the same things, but that I'll discuss with the help of question. First, write down this part, the derivation part, then I'll discuss the numerical based on this. But if you want to ask anything, any doubts are there, please get it clarified. Okay, let's solve the numerical then. See, these are two capacitors which are connected, and the voltage is also given. Individual capacitances are mentioned. So, see, we can directly see branching has occurred. It means the charge will get split and potential will remain the same. So, this shows that this is a parallel connection. So, in the first part, when we'll calculate the C equivalent, this will be simply C1 plus C2. So C1 plus C2 means 5 plus 10, that is 15 farad. This is the C equivalent. Means you can remove both of the capacitors and you can just write one single capacitor with the value 15 farad. Got it? When you have to write the C equivalent, it means you can replace all of the capacitors and just write a single value, that is 15 farad. This is what I was telling in the last class. Means you have these two capacitors, you remove both of these capacitors and you can just put one single capacitor. Okay, I'll just show the previous part. Okay. So yes, this I was saying. Now let's continue with it. So now total voltage. Again, the total voltage is present. Total voltage is given. 10 volts is given. So second part, the total voltage will be 10 volt. Total voltage means the supplying voltage. Supplying voltage means the voltage with which the circuit has been supplied. Okay. Third part says total charge. Now class, total charge means the charge that will come till here. It will get split. Further, it will get divided. The third one says we have to calculate the net charge, that is the total charge. For total charge, we are going to use again the same thing, C equivalent into the total voltage. That is 15 into 10, which is 150 coulomb. This is the total charge. Fourth part says voltage across each. Can anyone tell me what should be the answer of this voltage across each? First of all of you open the camera. In the class, you have to open the camera. And second answer for the total voltage, what do you think is the value? Total voltage, it's 10 volt. Individual voltages should be V1, V2. Will it be different? Do you think it will be different, the individual values?
No, ma'am.
Yeah, no. Means all the values will be the same. It's a parallel connection. So straight away, when you are calculating V1, which will be equal to V2, okay, and this will be equal to the total voltage. This time the voltage will not divide. Like in the previous part, we saw the voltage got divided. One received 20 by 3, one received 10 by 3. This won't happen here. This time the charge is going to divide, and you will see how. See, fifth part is charge in each. Let's calculate this first. See, one will be, you put C1, you put V1, you get the value of Q1. C1 now voltage is the same, it will be V only. So capacitance is 5 into 10, that is 50 coulomb. This is one value of the charge, that is the first capacitor. Similarly, you will put the value for the second charge. This will be C2 into V. That is 10 into 10, this is 100 coulomb. Just look, like in the previous case, voltage was getting split, and when you added them, you were getting the entire voltage back. Right now, if I add these two, 100 plus 50, I'll get 150 coulomb, which is actually the original charge. Means it means a charge 2 of 150 coulomb comes. It gets divided. One branch receives 50 coulomb, the other branch receives 100 coulomb. Till here 50 coulomb will come, till here 100 coulomb will come. Both of them will get added and back to 150 coulomb will be there again in this branch. These divisions and writing you will see more in the Kirchhoff's law, that is there in your current electricity. So we did it till Fifth part, na? हाँ. 6 says energy stored in each. See, for the individual energy stored, we can use half C1 V square. If you put C1, it will give you the energy for the first one. So this will be half into 5 into 10 square. So 500 by 2, it's 250 joules. For second one's energy, it will be half C2 V square. The voltage I am not changing because voltage's value is the same. I am just changing the values of capacitance. You put C1, you will get the data for C1. You put C2, you will get the data for C2. This will be half into what is C2? 10 into V square. What is V square? 10 square. This is 500 joules. Last part says the total energy stored. Now, total energy stored can be calculated. One method is that you know the individual energies between both the capacitors. C1 you know, C2 you know. Directly add them. That will give you the, ultimately it will give you the total energy. So, for the seventh part, total energy can be calculated as U1 plus U2. That is 250 plus 500, which is 750 joules. But plus, what if this part wasn't given? Directly the total energy was asked. Then it's not feasible to first calculate U1 and then calculate U2. It's just a waste of time. Why will you calculate U1 and U2? Directly use C equivalent. Just put the value of C equivalent directly. So here, or second is that if you use C equivalent, you will get it for the entire circuit. Half C equivalent V square will be half. What was our C equivalent? 15. So half into 15 into 10 whole square, that is 1500 by 2, which is 750 joules. So you'll get the same answer. Yes, is it clear?
Yes, ma'am.
Ali, Marwa, all right, write it down. Class done?
Oui. Finish.
Okay. This sharing of capacitors I'll tell later. Let us just complete yesterday the circuits which we were doing. Now, please go through them again because some of the things you might not have understood yesterday. Now, try to go through these. And Obedullah, now it's clear why this potential divider method had led to the same potential difference leading to the parallel combination. So, yesterday, what all, not yesterday, day before yesterday. So, day before yesterday, we had discussed this circuit. So these are in parallel. The resultant is in series, 15 and 10. So try to replace whatever capacitors you get with one single capacitor so that the final resultant you have with a single value. Then we discussed one more where six capacitors were present. So one, two, they were connected in parallel. Then the resultant was connected in series with it. Its resultant was connected in parallel with it. Finally, all three of them were connected in series. And one thing, as I've said already before, you put a battery whenever equivalent capacitance or equivalent resistance is asked. By this way, your solving of the circuit will become easier. At least it will give you where the circuit closes. So it will give you an idea where the circuit will close. Like this, you will have one single value of capacitance. Then I discussed short circuit also with you and an open circuit also. Now, one question based on potential divider method and short circuit. See this, look at this one. Here, if you see this part of the circuit, if I write down the individual potentials, here potential will be VA across this wire. Here potential will be VA, here potential will be VA. Now let me take the second one. If potential from here, so this is something else. Let me name this as VB only. So here this will be VB, this will be VB. So this is just the same thing. Whatever I have done it here, it's just the same circuit that is drawn. But you can conclude here that all these three are connected in parallel because the potential difference among all the three is the same. So how can we draw it? One capacitor connected here.
Ma'am,
Yeah, here whether say
how we recognize that potential difference is same?
VA minus VB, VA minus VB, VA minus VB, like this. Okay, take the difference. Take assume any one potential. One will obviously be at a higher end. One will be at a lower end. Let's say VA is greater. So it will be VA minus VB. Here also potential difference will be VA minus VB. This side also it will be VA minus VB. Okay. All right. These are the three capacitors having the value. See, now look, class, yesterday I told you a case. Can you tell me which one is this? Anyone who can recall, not yesterday on Tuesday we discussed. This one. Any one of you who can tell me. Will there be even a current through it or not? Means a charge passing through it or not?
Will not pass. So we should remove that capacity.
Exactly, very good. This is a short circuit. This one is a short circuit because you have connected a wire. This one, this circuit that is present, this is a short circuit. So you can replace this by just a straight wire. That's it. And then this will be present, which is whose value is C. So see, these are three parallel connected. So this will be 3C and this will be C, right? So 2, 1, 3C, 1C, they are connected in series. So how will you get the C equivalent? 1 by C equivalent will be 1 by 3C plus 1 by C. This way, this is equal to 4 by 3C. So C equivalent is 3C by 4. What have I done here in this? It's a combination. Here it's a short circuit. So I can just replace it with a single wire. No need to put the capacitor in your calculation. All these three were connected in parallel. So I've put them in parallel and the resultant is 3C. This was left, this capacitor, so that I have put here. They were in series, so answer is 3C by 4. First tell me class, is this clear?
But in last, it is looking like as if it is a series.
So series, I've put it as series only. This is in series.
Yes,
1 by C
but in
equivalent is
beginning,
for
it is
series.
parallel.
These were in parallel. These three, 1, 2, and 3. We don't know about this. It's connected in series with their resultant. Okay, their resultant is this 3C. I've replaced. That's why I say that replace all the capacitors with a single one. You know which all capacitors have been reduced. All these three are in parallel. We have put them in parallel. This one is in series only. So see, we have put it in series. This is this one. Okay.
Okay, ma'am.
And what about Quasar? Quasar, you getting it?
Yes, ma'am.
Okay. Please write it, all of you.
Ma'am,
Yeah, Ubaidullah.
this potential divider method I'm not able to understand.
See, potential divider methods, if you understand it from here, it will be better because it's the same thing. See, what you do, you take a potential. Let's say I have taken this potential, which is V. Potential will be here also VA at this side. Yeah. And see, this is a wire that has been branched over this side. A junction has been created. So this doesn't affect the potential. Potential doesn't get affected here. If it is traveling through here, it will travel completely through here and it will reach this point, right?
Yes.
See, again it will come here, it will be VA, but it cannot cross the capacitor here. It's not crossing. Here also it couldn't cross it, so it was stopped at here. And here also till here only it will go. So here all the VAs are set. We cannot put more VAs, right?
Yes.
Now let's assume the next potential VB, which we have to set. See, here it will be VB. Now through this wire, here again VB will go, and this point will be VB, this point will be VB. we have just put all the potentials. Now check the potential difference. Assume that one is greater. Let's say VA is greater than VB. If VA is greater than VB, then potential here difference here will be VA minus VB. Here also VA minus VB, you write it, na, higher minus lower. So higher minus lower,
Yes.
higher minus lower, higher minus lower. All the potential differences are same. It means it's just a parallel connection which is written like this only, but is put in this manner. It's actually this circuit which has been just modified in this manner. Now understood, Abedullah?
Yes, ma'am.
Okay, so same circuit has been put here. Okay.
But potential will be difference, I think.
Potential will not be
Potential.
VB. VB will not be there. That's what I was saying. Take some potential. It's random VB that I have taken. Because this potential VB will be till here only. It will be some other potential, but value will be the same. You can make it VC. Take any other variable. Because VB will be till here. Okay.
So value of potential will differ.
No.
But
This is, let's say, VC. This will also be VC. This will also be VC. So potential difference will be VA minus VC in all three of them.
yes,
It will be different from these two.
potential difference will be.
Potential difference is the same. Got it?
But potential is not same. But
Potential
potential difference is same.
for capacitor, you take the potential difference on, no, because two plates are there, and one side has been charged positively, one side has been charged negatively. So two capacitor plates are there. Each have their own potential. So you always take the potential difference. Okay?
So it is not a single
It's not a
circuit like before.
single circuit means.
Before the potential was same at every point, but here the potential is different. For example, VA is not equal to VB.
Okay, potential difference means VA and VB. They won't be same. It's not necessary. It can be same also, but difference will be the same. Even if they are same, VA and VB can be same. That's a very specific case. Okay, and that won't affect your answer. Potential will affect your current, your terminal potential difference, and your EMF of the cell. These will affect your internal resistance and all. But for charges, it won't affect because two capacitor plates are just present. One plate is positively charged. Now, due to the process of induction, this becomes negatively charged. Like this, the charges flow. So potential of this plate is present, potential of this plate is present. So we compare these two actually in this method. And it's just a very specific method for this one. Like this is not a very general method you can apply for every circuit. No. See, circuits have a lot of techniques to solve, lots of techniques. And even when you study for your competitive exams, various methods are there. Symmetry method is there, this method, that method. So this potential divider method is exclusively valid for this circuit only. All right, for complex circuit, when potentials will not be there or if they are same, we'll not use the potential divider method. We'll use some other method. Okay.
Yes. So it is a special kind of parallel combination.
Yes, it's a special kind of parallel combination, nahi, but a special arrangement. Special arrangement, a typical arrangement, this one, where for solving of which you can use this potential divider method. Okay. Don't use it generally for every question. You'll not be able to do. Sabka potential different hoga fir to. Okay.
Yes.
Written.
Right.
Okay, let's see some other method. See, there's a case which is known as Wheatstone bridge. So again, I'm clarifying this. This Wheatstone bridge is also one specific arrangement of all the capacitors. Now, class, Wheatstone bridge from capacitors very rarely come. Okay, recently also, I think Wheatstone bridge question has not come based on capacitor till now. It's included in your syllabus, so you have to revise it once. But Wheatstone bridge based questions are often asked in your board exams in from your resistors. So we'll do it in detail in resistors. We'll do the derivation also in the resistor. Right now, since it can be possible, let's see what is the Wheatstone bridge. This arrangement is called as a Wheatstone bridge. Basically, 5 capacitors will be there. Two, see, all these are connected in the form of a quadrilateral. Okay, this is a quadrilateral, and one capacitors are present, and one capacitor will be connected diagonally, which is not joined to the battery. See, A point, C point, these are connected to the battery here. B point and B point, this is not connected to the battery, right? So here you will have the fifth capacitor. So Wheatstone bridge derivation and everything detail, we'll do it in the next chapter only because it's a waste of time to do it here. It won't come from the derivation perspective. But let's just see in case your exams are there or you want to prepare. There is a balancing condition of the Wheatstone bridge. Basically, this balancing condition means you take the ratio, all of these have their values. If the balancing condition is achieved, then only you're going to use this formula or whatever I'm going to say. Balancing condition, you have to first decide whether your bridge means this whole arrangement, is it balanced or is it unbalanced? How will you check? C1 by C2 should be equal to C3 by C4. This ratio should be the same. Like if I give you one one value of C1, let's say as 4 farad, and I give you C2 as 8 farad, and I give you C3 as 3 farad, and I give you C4 as 6 farad. When you will take the ratio of C1 by C2, it will be half. C3 by C4, it will also be half. So you can say, yeah, now your Wheatstone bridge is in balanced condition. So if it is in a balanced condition, you can change its arrangement. In the sense, when the bridge is balanced, class, the potential difference here across this one, which is not connected to the battery, it becomes the same. VB will be equal to VD if the bridge is balanced. And if the potential difference becomes same across here, the difference is zero, and this wire you can simply remove and just delete this wire from your arrangement. So how can you draw this then if this middle wire is not present? Like this. Let's say this is C1, this is C2, this is C3,
If
this
ratio is
is,
zero, then
difference is zero. Ratio will be there, but ratio is equal. Okay.
yes.
Now this is there. So you replace the middle wire. Just remove it as if it wasn't there in your circuit. Now you will be able to solve it. See, very easily. I hope it's easily identifiable for you also. C1 and C2, how are they connected? Series or parallel?
Uh, Series, I think C1, C2 series.
Yes, Vedula, right. C1 and C2 are connected in series. Why isn't it clear for others? The same thing, C1 and C2, this is the same wire, it's just it has bent. So C1 and C2, these two are connected in series. Marwa, you tell me, how are C3 and C4 connected?
Yes, ma'am.
How are C3 and C4 connected?
Series.
Series. Very good. They are also connected in series class. Ali, can you tell me how are their resultants will be connected? Series or parallel? Parallel. Very good. They'll be connected in parallel. So their resultant will be connected in parallel. So this is how this question can be solved. Okay. Just write it down. Then we'll see something exclusively for capacitors because this is a general one. This is related to your more to your current part, but this arrangement can be asked to you. Okay. Write it. These kinds of circuits we'll practice a lot in your resistors. Write it down. Then let's see some more circuits.
Ma'am, this is under condition of balance.
Yes, only if it is balanced. If not balanced, then this method is not valid. Okay. See, there are certain problems involving plates. So this is exclusively for your capacitors. You will just get it for capacitors. They will give you, the question will give you certain metallic plates. Let's say this is one metallic plate in this manner. Let's say there is one more metallic plate which is present like this. These are certain plates present. This is A point, this is B point, and here you have to find out the equivalent capacitance. That's it. It will just give you the plates and it will ask you the equivalent capacitance like this. Nothing will be mentioned. So how to tackle these questions? Do one thing, immediately connect a battery between the A point and the B point. Now, this is the positive terminal, this is the negative terminal, class. Whatever is the positive terminal, it will make this plate completely positively charged. So this will be positively charged. This plate will be thoroughly positively charged. Whereas this plate will become negatively charged. Entire plate becomes negatively charged. Okay, now what you do, you just have to identify the number of capacitors plate. Okay, class, again I'm saying this is just a single case. If you get this, this is the only method how to solve it. Okay, this is just for that purpose. This is positively charged side, this is a negatively charged side. See how many charged sides you have now. If you see here, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. Now see, you have to identify the number of capacitors. One plate is not forming any capacitor plate. It's just a single plate. Single plate will never form a capacitor plate. 2 and 3, see, both of these, they are separated by a d distance. Let's assume they are separated by a d distance. This will form one capacitor plate, positive plate, negative plate. This will form one capacitor plate. Then the fourth one and fifth one, again, they are oppositely charged. They are two plates. They, let's say they are separated by d. So this will form a second capacitor plate. The sixth one and seventh one, they will form one more capacitor plate. So three capacitor plates are there. This will also not form. This will also not form. Whatever is the number of capacitor plates, your C equivalent will be that times epsilon naught A by D. That's it. This will be the answer. Okay. Straight away, if you are able to form three capacitor plates, 3 epsilon naught A by D. This one is clear. Then I'll give you one more example. Is this clear?
Ma'am, this counting I'm not able to understand.
Counting, you have to do this way. You have to identify one positive side, one negative side. If you are able to identify this, count this as 1. Okay? Like this.
Yeah.
1, this was 2, this was 3. I'll give you one more example. See. Like this. These are x and y ends. Suppose they are connected to the battery, and after that only they are charged like this. This is the positive terminal, this is the negative terminal. So this will make this plate completely positive, it will make this plate completely negative. Now look, see positive and negative, this will form one capacitor. Thus, will this form a capacitor? Yes or no? What do you think?
No, I think.
No, it won't form, right? This won't form. Because these are both are negative. Again, this will form. Only two capacitors are there. So C equivalent will be 2 epsilon naught A by. This is how you have to identify the number of capacitors and just multiply it with epsilon naught A by D. Is that clear to others also? Marwa, Kausar? Yes.
Yes, ma'am.
Okay, then write these two. There is one more case regarding the slab that I'll discuss. But first, write down these.
Ma'am, can you scroll up? Uh,
Okay, class, let's discuss the dielectric slab. There can be questions on the dielectric slab also. That see, this is one single capacitor. This is the main capacitor. In that one main capacitor, two dielectric slabs have been put. That equivalent, see, it will obviously disturb the equivalent capacitance. C1 will be different, C2 will be different. Within this, two different capacitances will be present. So this is one single capacitor whose value has been changed due to insertion of dielectric slab. All right, are you getting that this is one single capacitor? Now class, how to identify whether it's in series or it's in parallel? If the area is getting divided, it's a parallel connection class. If the distance is getting divided, it's a series connection. Look here, the distance between the plates is remaining the same d, while the area has been divided. Causar, will it be parallel or series connection here in this? Parallel connection, yes, right, because area is getting divided. So how will we solve the parallel connection? Okay, we just know that it will be a parallel connection. Calculate the individual capacitances. C1 will be C. For dielectric slab, we know C1 is going to be K1 epsilon naught. Area is A by 2. So this will be A by 2 and distance is D. C2 will be K2 epsilon naught A by 2D. Now they are connected in parallel. So C equivalent will be simply C1 plus C2. K1 epsilon naught A by 2D. I hope you know why 2 is there because area is A by 2 plus K2 epsilon naught A by 2D. So here we'll take for C equivalent, we can take epsilon naught A by 2D out common and we'll be left with K1 plus K2. This is the C equivalent. Clear? Is that clear?
Yes, ma'am.
Okay, please write it.
Ma'am, what is K1 and K2?
Dielectric constant. We write the formula of capacitance, no? The general formula K epsilon naught A by D when dielectric slabs are present. These are those. Okay?
Yes.
Okay, done. Okay, Ubaidullah, can you tell me in this, is it connected in series or parallel?
Series.
Yes, very good. They are connected in series because distance is getting divided. By this, you will be able to identify the exclusive cases are these only. See, these will not be repeated in the resistors, right? Because these are just exclusive for the capacitors. So when you are calculating C1, it will be K1 epsilon naught A by D by 2. C2 will be K2 epsilon naught A by D by 2. C2 goes up. So C1 is 2K1 epsilon naught A by D, whereas C2 is 2K2 epsilon naught A by D. Now, as he rightly said, they are connected in series, so you will reciprocally add them. 1 by C equivalent will be D by 2 K1 epsilon naught A plus D by 2 K2 epsilon naught A. Because you are reciprocally adding them. It's in series connection, right? So in series, let's take D by 2 epsilon naught A common. It's common in both of these, 2 epsilon naught A. So we'll be left with 1 by K1 plus 1 by K2. Let's take the LCM of this. 1 by C equivalent will be D by 2 epsilon naught A. This will be K2 plus K1 divided by K1 into K2. Why did I solve it till here? Because I wanted the reciprocal value. This is 1 by C equivalent. So C equivalent will be D into K1 into K2 divided by 2 epsilon naught A K1 plus K2. This will be the final value. Is that clear? Everyone? Ali, you're understanding?
Ma'am,
Yeah, Ubaidullah, say.
we did reciprocal, right? 1 by
We did.
this. Reciprocal.
किया तो यहाँ पे. See, we have taken the reciprocal. What are you asking, Ubaidullah? Can you just repeat?
We did reciprocal to 1 by C equivalence.
Yes, yes. Because see, this answer is 1 by C equivalent. You don't want 1 by C equivalent. Why will you get this? Right. So this since it is the formula we obey till here. But then we can take the reciprocal. So this will give us C equivalent by 1. That's what we want. Okay.
Yes, ma'am.
All right, write this.
Ma'am,
Yes, Ubaidullah.
uh, this diagram I'm not able to understand.
Diagram, see, diagram is like one single capacitor is there, like this, which is connected to the battery. Okay, this is one single capacitor. I just enlarged it. Here, instead of putting one dielectric slab that we usually used to have, two dielectric slabs have been put, like one like this, second like this, which is K1, which is K2. This is what is wrong. Got it?
Uh, that on same capacitor, how that positive sign also and negative sign.
Induction, method of induction. We discussed the methods of charging in our backup class. That time we have induction. This is positively charged. Charges never flow like this. In between, the insulating material is present. So how will the charge flow? That's the condition for forming a capacitor we discussed. Two conductors oppositely charged with dielectric medium between them. So charge cannot flow through it. So how does the charge travel? One side becomes positively charged through the method of induction, which we have studied in our backup class, first backup class. The second one becomes negatively charged. It will induce a positive charge on the other side, which will induce a negative on the other side. Okay, so through the process of induction, the charges have traveled. That's why one is positive, one is negative. Okay, clear?
Yes, ma'am. That center
Well,
of
I think you missed that first class, no? Backup. Or you were there.
I think I was absent.
You were absent. Yeah, the first backup class. Take the video lecture at least for it. Just text the operation team of Learnivio. They'll provide you with a video. At least watch the video because the methods of charging are very basic. Method of conduction and method of induction. Induction is used throughout the capacitor. Conduction is used in your Coulomb's law. Class, just let me know done. See, this topic is done. One small topic is which I was mentioning in the last class, that sharing of capacitors can be asked. So that formula I want to discuss with you. So just text me a done so that we can discuss that and this chapter is done. Class done.
Ma'am, I'm not able to understand calculation. Last step.
Which step? This step. Hmm?
Yes.
See,
Last.
clear, is it clear?
Yes, ma'am. Only last one.
Okay. See, when we took the when we took the LCM here, so K1 into K2 was it there? Okay, I've written it opposite. Wait. This must be the confusion. It will be 2 epsilon naught. Just wait. 2 epsilon naught A by D will come up. 2 epsilon naught A because we have K1 and K2 with this, no? So K1 into K2. K1 plus K2 have this T. Now clear, Ubaidullah? I actually wrote by mistake the opposite.
Yes, ma'am.
Okay. Please just make the correction, class. That was incorrect, which I wrote before this. I by mistake took 2 by a D above. Now done.
Wait.
Marwa, Ali have completed. Kausar and Ubaidullah, are you both also done?
Yes, ma'am.
And what about Kausar? Just one small topic is there. It's just that the derivation is not included in your syllabus, which has been recently deleted. All right, that has been recently deleted. So we discussed it till here. Spherical capacitors, force, energy, density. Yeah, sharing of capacitors. C class, sharing of capacitors, the derivation of the loss of energy has been deleted. But I have the derivation written on the screen. So if anyone wants to take the screenshot, just let me know. Not this one. See, Ubaidullah, I was referring to this. This is like the method of conduction. So please just take the first lecture, at least. Of course, sir, your backup wasn't given of any class. But rest of the students, Marwa also had. Marwa has attended the class. See, when different potentials are present, and you the conductors or capacitors both. Remember, in the first class of capacitance, I told you that capacitor is just a conductor which holds charges. So you can use spheres also. So if these conductors are present which have a different value, let's say V1 is greater than this V2. So V1 has a higher potential, V2 has a lesser potential. When you connect them, the charges flow until both of them have the same potential. Till the time both of them don't have the same potential, the charges flow. Once the same potential is reached, the charges stop flowing them. This is what is meant by sharing of capacitors. Some amount of charge gets transferred from the higher one to the one which has the lower potential. The charges will always flow from higher potential to lower potential. This is the whole theory part behind it. Means charge just travels from one conductor to another conductor till the time both have the same potential. Like, let's say this had 5 volt, this had 3 volt. Some charges will travel, potential will change. Let's say this became 4 volt, this reduced to 4 volt, this increased to 4 volt. As soon as 4 volt is reached in both of them, the charges stop flowing. This is what is meant by sharing of capacitors, sharing of conductors. Sharing of conductors, usually this happens. Coming to capacitors specifically, let's say this was the capacitor C1, potential was V1. This was before sharing. You have not connected them. You have just taken it and you are just taking its data. C1 is there, V1 is the potential. The charge will be C1 into V1. Energy will be half C1 V1 square. This is before sharing. And what about C2? Charge will be C2 V2. Energy will be half C2 V2 square. Okay, all these things are before sharing. Once you connect them, what did we study? The potential becomes the same. So both of them this time will have the same potential. Q1 prime, let's say this Q1 dash is the new charge, it will be C1 into V. Energy will be half C1 V square. We are not using V1 and V2. The potentials are the same. They have reached a common value after sharing. The sharing means after getting connected, some charge must have traveled from the higher to the lower one till the time both of them didn't reach the same value of the potential. First, tell me this before sharing, after sharing part is clear, and is this part clear? Or anything you want to ask? Anyone? Clear or not?
Yes, ma'am.
All right. Sir, you have to be a little interactive with the classes, okay? At least start responding in the class, Kauser. And if you have any queries, you are free to ask. Okay. See, this is the whole theory that is written on connecting two capacitors. Charge flows from one at a higher potential to the lower potential until they acquire the same potential. This is what is meant, what we have discussed. Now, if charge has just traveled from one to another, we have not added charges, we have not deleted charges. Right? Charges have been just traveled from one to another. So total charge will be the same. If 3 coulomb has traveled from this end to that end, total charge, whatever it would have been, it would be the same. So charge before sharing would be equal to charge after sharing. So you can say C1V1 plus C2V2 is C1V plus C2V. V becomes the common potential. That is C1V1 plus C2V2 divided by C1 plus C2. This is the common potential. So for solving the common potential, you can use this formula, but this step is very important. If you are able to write this step every time, you'll be able to get this formula correct. Even if the questions give any change or something, you will be able to do that in that step. If it adds some charge or it does anything, you can just replace in this. So this step is very important. The second one was this loss of energy. See class, loss of energy means initial energy minus the final energy. So this entire derivation is there, which has been deleted from your syllabus. So if anyone wants, he can take the screenshot, but it's unnecessary. Okay, it's completely unnecessary because those who also have to appear for their competitive exams, you don't need any derivation. See, like this, I told you here for common potential, write these steps because this step is crucial. There isn't any step in the derivation of loss of energy that is crucial for solving the questions. So this is the derivation, but the formula is included in your course. And formula is delta U is basically C1 into C2, product of both the capacitances, into the difference in the potential square. Now, if V2 is greater than V1, then write V2 minus V1 whole square. If V1 is greater, use V1 minus V2 whole square because anyways it's squaring, so it will be positive value. Divided by 2, C1 plus C2. Divided by 2, C1 plus C2. C1 into C2 into V1 minus V2 square to C1 plus C2. This is it. Okay, this is the formula for it. So just remember the formula based questions only come. Yeah, earlier this derivation was there, now it's not there. So this sharing of conductors, sharing of capacitors is clear. Start writing, please. Okay, Marwa.
Ma'am, can you ma'am, what is Q1 dash?
Means the new charge after sharing. So they are connected.
Ma'am, what is difference in UV? First is 1 by 2 C1 V1 square and one is 1 by 2 C1 V square.
Yes, the potential has changed. Na? Now the potential is a common one, which this potential, which has become same now.
Yes, ma'am.
Okay. Before sharing path, you have written Ubaidullah. This one.
Yes, ma'am. Ma'am, this is diagram, ma'am.
Ubaidullah, done with this part.
Yes. Ma'am, can you scroll up?
Ubaidullah, have you done this part, the writing one?
Yes.
Ubaidullah, Ali, just take the screenshot of this page if you have not written it till here and the formula below. This one also. Just take the screenshot of this formula or write it. Ubaidullah, if you can write it, you can write. Ali, also you too. Otherwise, class, you can leave. In the next class, we'll just continue with current electricity.
Yes.